Hello everyone and welcome to the NPTEL course in Herbal Drug Technology. So if you recollect, in the previous sessions we saw what is standardization, and standardization is a way to ensure consistency in the product such that it retains its purity, efficacy as well as consistency over a period of time. Now we saw different methods of standardization like your physical, chemical, biological. The main activity of the herb is due to the phytochemical presence in it, and as a result this subsequent sessions will be focusing more on the standardization of these herbs based on their chemical constituents. Now as we know, drugs contain, say for example, Vasaka, Adulsa, Jeshtimat. There are many herbs we consume on day-to-day basis for their therapeutic benefits, and they contain different class of compounds. These compounds include your alkaloids, glycosides, steroids, terpenoids, resins, flavonoids, lignans and many others. So what do we do? Whenever you have to standardize, we take an approximate that the major activity of this compound or the major activity of this herb is due to which set of compounds or which combination of compounds. Thanks to modern pharmacological research, it has now been possible to elucidate that, and then once we know that which compounds are responsible for the therapeutic activity, it is best to standardize this herb in terms of those compounds, because the concentration of that compound will determine the overall efficacy of the herb. So let's start standardization of herbs with suitable examples. In this particular session, we'll be doing standardization of Vasaka using UV-Vis spectroscopic method as well as chromatographic method. So Vasaka, as you know, often referred to as your Adulsa or a Malabar nut, is actually a leaf based drug. So we pick the leaf from the plant called as Adhatoda vesica or often Justica adhatoda, which belongs to the Acanthaceae family member. Now this is a plant which is abundant throughout India and grows in a typical tropical climates of Southeast Asia. Nowadays many of the people have switched from allopathic cough syrup, knowing their toxicity especially in children, to modern day formulations containing Adulsa. So you don't eat Adulsa kada or you don't drink Adulsa kada, but you prefer to have Adulsa syrup, which is herbal, safe and as a result found to and also efficacious. Now if you go to see the chemical constituents of Adulsa which are responsible for therapeutic activity of Adulsa are a class of quinazolin alkaloidal compounds called as Vasacin as well as its ketone derivative. So this is a quinazolin alkaloid Vasacin, and over a period of time it gets oxidized to get a ketone derivative of Vasacin. So they just differ by a ketone moiety, and that's your Vasacinone. So Vasacin and Vasacinone are the compounds which are the quinazolin alkaloids, but they are not just two. There are many other alkaloidal compounds present in trace amount in this drug. Now apart from that, you will see alkaloids such as your Vasacinol, Adhatodinin, Adhavasacinone and so on. Just to mention a few, but like I said, there are many more. It contains your triterpenoidal compounds like your beta-sitosterol, glucosides, camphorol, and if you go to see standardization perspective, now the need for standardization comes from a very good observation that even you can do nowadays. So if you go to a chemist shop and ask him for or ask her for a Adulsa based syrup, because it is used for cough. So if you ask any cough syrup containing Adulsa, you will see numerous pharmaceutical as well as Ayurvedic companies have come up with Adulsa preparations. Now the twist is, if you read the label of these bottles, you will see some of them will contain Adulsa extract, some of them will have Adulsa powder depending upon the formulation, of course. But if you see the dosage, you will be surprised to see the doses coming as low as 50 milligram to as high as 300 milligram. Now this is a huge variation and definitely needs to be standardized also in terms of efficacy, that what dose is it efficacious. Now whenever an industry is claiming that they have added 300 milligram of Adha Toda Vasaka powder, how am I going to quantify that? Now you can quantify by taking an empirical concept, that is approximate vasicine and vacicinone content. So approximate vasicine or vacicinone content you can count as up to 0.85% of the leaf weight, that is the dry weight of vasicine, and 0.027 or 0.02% of the dry weight of the leaf basis it contains your vacicinone. So vasicin and vacicinone are the two important phytochemical markers which can be used for standardization. Now that you know these alkaloids are active and can be used for standardization, how do you do standardization? So for standardization we need to quantify these alkaloids present in your powder, that is your raw material, as well as in the formulations. So if you go to see formulations, you might have formulations such as your Vasaka powder, Vasaka capsules, this is your Vasaka Vati which is just pressed tablets, or nowadays like I said you get your Adulsa syrup. So you're going to take these samples and do a analysis. Now the methods of analysis generally are quantitative methods. The reason being we want to quantify. So quantitative methods will tell us how much is the content. Now you can do it in a two-way. You can do a non-specific quantification. Non-specific quantification is, since I know my alkaloids are active and vasicin is a major alkaloid, why don't I estimate total alkaloidal content? So non-specific method for quantification of alkaloid is done generally using UV-Vis spectrophotometry or UV-Vis spectroscopy. Whereas if you want to specifically quantify vasicine and vacicinone content, you can go to little expensive but very reliable chromatographic methods, which are your high performance thin layer chromatography, whereas the second one is your high performance liquid chromatography, also referred to as high pressure liquid chromatography. So HPTLC and HPLC are two methods which can help you in quantification of specific phytochemicals present in your formulation. So let's first study and analyze non-specific method. We'll just restrict to one case, but there are many abundant methods of doing it. So the UV-Vis spectroscopy or UV-Vis methods rely on only one thing or one parameter, and that is how much light it absorbs. So you can either measure absorbance based on how much it absorbs or the transmittance. So typically UV-Vis spectrophotometer has a light source. This light source can be a halogen lamp for visible and a deuterium lamp for a UV range. Then you have a collimator which can help use or which can help refine linear or planar light for us. Then this is going through a prism or grating where these waves will be split into spectrum, and from which you can pick up the wavelength of your interest. So this wavelength of our interest is the wavelength at which your compound, say for example vasicin or a particular structure, absorbs maximally. Now this sample will be kept in the cuvette or a small glass quartz glass vessel, that is your sample will be irradiated with this specific wavelength. Now this sample will absorb some light and then the remaining will be transmitted. Based on the reduction, it will tell you in terms of output that how much quantity of your light was absorbed. So you can see here, in case of your alkaloids, if I just take that sample, put it in the quartz glass tube and run the UV. You can see here this UV runs at different wavelength. So I have kept a range starting from, or I have kept a scan, it is more specifically called, from 200 nanometers. It is scanning the absorbance, how much light it is absorbing, to all the wavelength till 600 nanometers. So what is observed is, if I just put my pure Vasacine as a compound, you can see there are a lot of conjugated double bonds, and this conjugated double bonds are responsible for the absorbance of this quinazoline alkaloids. So this conjugated double bond is going to give me a high, and this is called as the UV maxima or absorption maxima of that compound, which is close to 302 nanometers, and thereafter it starts decreasing. What does it mean? That beyond this it doesn't absorb any other wavelength. Whereas instead of pure compound, if I put the whole plant extract, which is mixture of compounds, and say specifically in this case they have added methanolic extract. So they saw that this methanolic extract, because it's rich in alkaloids, you will see a very close alliced behavior with a little UV max at 251, then another UV max but a slight shift at 305 nanometers, and thereafter again a decline in absorbance, saying that there are other compounds which are absorbing but the absorption is minimum. So whenever I have to do analysis of this compound, a good wavelength is somewhere between 302 to 305 nanometers for Vasacine. Now the point is, this Vasacine is, when I do it pure, it's good. Sometimes in extracts definitely I can do it in this manner, but imagine I have a polyherbal formulation. Now polyherbal formulation contains many herbs. So what happens therein is, it is going to contain other compounds as well, and it can so happen that this other compounds will have this value as a UV maxima. As a result, what will happen is, I will get a very false reading for a quinazoline alkaloid. So I have to be very careful here, and that is the reason they do something called as derivatization. Now derivatization is a process of converting these phytoconstituents into more intensely colored products, and what happens is, because now they are more intensely colored products, their absorption shifts from UV region, which was this, to more color region where other compounds also do not absorb. Imagine a hump out here. So imagine here also the extract, even in extract there is no compound absorbing in this region or very little. So if this hump would have been here, the absorbance due to other compounds is minimum, and that's the reason they do derivatization in your UV-Vis spectroscopy. So we'll study a method. Now this method is called as determination of alkaloids by bromocresol green. Now bromocresol green is a dye which has a ability to bind. Now if you study this graph, again I am just putting it here. If I see my alkaloids mainly absorb in a 302 to 305 nanometer range, and mostly my visible range was coming a flat line or a very minimal hump. Now when I react it with bromocresol green, it forms a ion pair. So both of them, bromocresol green is a negatively charged ion, whereas your alkaloid is a positively charged ion. So both of them will form an ion pair, and what happens is, you can see here, so where earlier there was a flat line, now you see a little hump, and that hump is specifically for alkaloids because there is no other compound which is absorbing in that region. So in bromocresol green method, what do? Is we first do a standard curve to see if alkaloids behave in this manner. So you can accurately disperse say 10 milligram of your Vasacine in your 100 ml alcohol, and from that you are going to take measured aliquots like 0.4, 0.6, 0.8, 1 ml, 1.2 ml. Okay, this solutions you are going to take, and to that you are going to add a slightly acidic buffer. Now this acidic buffer will convert alkaloid into alkaloidal salts. So now I have my alkaloidal salts, then I react it with about 5 ml of bromocresol green dye. So I have my alkaloid, then I made it acidic to convert it into salt, then I reacted it with bromocresol green. Now the bromocresol green complexes are being formed. Here I have one advantage. Once this alkaloid forms complexes with bromocresol green, this bromocresol green alkaloidal ion pair is soluble in organic solvent. So initially I have phosphate buffer which is water based, and now I am extracting it with chloroform. So I just subsequently extract with like 1, 2, 3, 4 ml of chloroform, and I pool all my washings together and put it in volumetric, make up the volume to 10 ml. So now from that 0.4 ml whatever alkaloid was there is getting transferred to 10 ml bromocresol green solution in chloroform. This, when I put it under UV absorption at about 470 nanometers specifically, what I get is an absorbance reading of how much complex formation has occurred. Now I can do a standard curve. Say for example, this is the absorbance, this is the concentration. So I can do 10 microgram, 20 microgram, 30 microgram, 40 microgram and so on, and depending upon how do I get this, I can plot my standard curve. Pass a line or a best fit line passing through the standard curve, and then you plot absorbance of unknown. You will automatically extrapolate it down to get the concentration in your alkaloidal extract. So this is how it is done. And you can see here, even in this case, you do an alkaloidal extraction. How do you do alkaloidal extraction? Depending upon the stability of alkaloids. Now generally alkaloids are very stable, so you take the plant drug, pulverize it very fine. Generally sometimes this can be done with a ball mill, with an ultrasound, or if you don't have, you can use a mixer grinder, but ensure that you don't overheat and char your powder. Now once this ball mill has pulverized your drug to a very fine consistency, sometimes the drugs are sticky. So in that case, when your drugs or formulations are very sticky, they are freezed first using a deep freezer to about -20 to -30 degrees Celsius, and then that cold ice preparation is subjected to ball mill to get a fine powder. This is then extracted with about 2 normal HCl 2-3 times, so that all the alkaloidal get converted into alkaloidal salts and then they occur in the solution. Now this alkaloidal salt is filtered, collected and washed with chloroform. The reason for this is alkaloidal salts are not soluble in organic solvent. But imagine if you have a adulsa leaf. The adulsa leaf will have pigments such as your xanthophyll, chlorophyll, and all of them are lipophilic and soluble in chloroform. So the moment you take this extract, that is your 2N-HCl extract, and partition it with chloroform, majority of your pigments will get transferred to the chloroform. So wash it as much as possible so that all the pigments are gone and your chloroform washings are colorless. The reason for this is you're subsequently going to add 5 ml of bromocresol green solution. Now when you add bromocresol green and phosphate buffer, it is going to form a biphasic mixture. Take it into your separating funnel and collect your chloroform layer, which is containing your alkaloidal bromocresol green complexes. Once that is done, give it 2-3 washings, like I said, with 1 ml, 2 ml, 3 ml, 4 ml. So if you just add this 1 plus 2 plus 3 plus 4, you should get a total 10 ml chloroform. So if it is not 10 ml, don't worry, you can just give it a little washing and make up the volume in your volumetric flask. So this volume is made up to 10 ml, and then this solution is measured at about 470 nanometers to determine the alkaloidal content based on the calibration curve that we prepared previously. Now this is non-specific, this can be done for numerous alkaloids, but it is seen that many a times alkaloids, especially those of amine types, alkaloids especially those of amide types, cannot be really estimated. Now moving on to the next one. The next one is when we do a specific analysis. Now this specific analysis means I am analyzing one compound at a time. So when you are doing this, you require chromatography for separation of compounds, which we didn't do in the previous method, and as a result this is classified as a specific method. So you are going to take your adulsa leaf, convert it into a fine pulverized powder and then macerate. Okay, you can macerate in your hydrochloric acid to convert it into salt, and then what we did, you remember this, you all extracted it with chloroform so that all the pigments are gone. Then you can do one thing, you can again basify it. The moment you basify the alkaloids, all of these alkaloids are going to get converted into free bases and they will be chloroform soluble. So even without bromocresol green, your alkaloids just by addition of base will become lipophilic as they are unionized, and you can use chloroform to partition it. Partition it with equal quantities of chloroform 2-3 times, concentrate it, prepare a 10 ml solution and use this solution for spotting. Now this spotting is done on a chromatographic plate, specialized plate which are called as thin layer chromatography. The reason it is called so because there is a metal backing like a metal foil, and on that you have a layer of your stationary phase. This stationary phase is your silica. About just very thin, somewhere like your 0.2 millimeter or so. Now this silica gel, what is done is you spot your compound here and dip it in the mobile phase. Now this is generally kept in a saturation chamber in presence of a mobile phase. The reason why we need to keep it in a saturation chamber because your mobile phase generally is a organic solvent. Now this is something we call it as our normal phase TLC. In normal phase TLC we use a stationary phase which is polar and a mobile phase which is non-polar. Example of non-polar solvents can be your hexane, ethyl acetate, toluene and so on. Now this majority of non-polar solvents are volatile in nature. So if this is not a saturated chamber and not closed well, this volatile solvents will escape, and sometimes when you are using combination of these solvents in a mobile phase, their ratio might change. Now what happens is if the ratio of this substances or the ratio of this solvent changes, you are going to observe a change. Now when I have spotted my compound here and when the solvent is running, based on its affinity for stationary phase, it moves along as you can see here in this graph, and it will separate, being most non-polar compounds being at top and most polar compounds not running at all, and in between polarity compounds come out here. So what is going to happen is, imagine after running 50% if the mobile phase composition changes and the mobile phase suddenly becomes more polar or more non-polar. So in that case, now they stop at a particular place, we call it as the retention factor or the RF. The retention factor is actually the distance travelled by your solute, say for example here, upon the distance travelled by your solvent. So I can put it as 1 and 2. So RF, I can just say, or I can put it as A and B. I can say RF is equal to A upon B. So the moment my mobile phase composition changes, my A upon B is going to be different. It's not going to be consistent and will cause problem. So this for plate development, saturated mobile phase is required. Once I have a plate ready, I scan the plate. Now this scanning is done by intensity, and that is called as a densitometric scanning. So you can see the most darker intensity comes here, and as a result the densitometer shows very intense bands in this particular region, whereas at the end they are very lighter bands, and here as well. So depending upon the RF you will get an intensity, and this is what is called as densitometric scan. Now once I have a densitometric scan, what also I can do is, You can see here 1, 2, 3, 4, 5 as very light spots. So I can take like 1 microgram, 2 microgram, 3 microgram, 4 microgram, 5 microgram, 6 microgram, and then I will see how much is the area under curve of this. So area under curve of this of different microgram is going to be different. So I plot concentration versus area under curve graph, and based on that, whenever I plot the unknown, I can always get the concentration. So this is how it works. I'll give you a few examples. So in this case, you can see here, this is a typical TLC of your Vasaka. Herein what they have used is a mobile phase, that is dioxane, toluene, ethyl acetate, methanol, ammonia in a ratio 1.5 to 1.3. Now mostly you will see alkaloidal mobile phases use base for the reason they have to be kept unionized. Now the densitometric scan, you can see it's brought in here, and you can get an area under curve for Vasacin. You can apply your extract and see how much Vasacin it contains. Now this Vasacin, how do I know that the spot is of Vasacin itself? Now HPTLC also gives me one more option, is I can selectively pick that area which we saw previously. This area I can selectively pick up as a peak, and then for this peak I will check the UV spectra. So I have put a UV spectra of my sample extract versus Vasacin standard, and both the UV spectras match. What does that mean? That means it's a singular compound, and that compound is your Vasacin. So I can also identify as well as quantify using HPTLC. So you can see here there is one more paper showing amount of Vasacin and Vasacinone. Now in this case, what is quantified is Vasacinone, which has a slightly lower RF, and they have done it in plant tissue cultures. So plant tissue cultures of leaf, stem, in vitro and in vivo, as well as the callus cultures. So you can see here they have checked it for the ability to do or quantify Vasacinone from it using a mobile phase toluene, butanol, butyl acetate, and still they could get a good resolution. And based on that, you can come to know that this densitometric scan has the highest area. So the third reading, that is the in vitro leaf sample, has the highest amount of Vasacinone. That is also one way how my HPTLC can help me. Now another method for determination of Vasacin and Vasacinone is by HPLC. HPLC often referred to as a high performance liquid chromatography or high pressure liquid chromatography. The reason is, imagine you take your TLC stationary phase and then pack it in a column and reduce the particle size to a very fine size. What is going to happen is you are going to get better resolution or better separation. But when the particles are fine, passing a solvent through that often is a problem, and as a result you will require a pump. So this mobile phase is actually pumped and pushed inside this column or a pipe-like structure which is filled with the stationary phase. Now once it goes inside the stationary phase, your compound is going to resolve into compounds like your Vasacin and Vasacinone, which will then be analyzed into same UV or what is called as your PDA detector. So what will happen, say for example, this was your Vasacinone and this was your Vasacin. So you will have two separate compounds coming in. They will travel separately. So first thing, your Vasacin will come out, will be detected, and second thing, your Vasacinone will come out and be detected. Now they are detected in form of a peak. So this peak will have peak height, peak area, that is also like your area under curve in a way very similar to your densitometric. Then you have a dead volume. Now this is just like if there is nothing injected, your plain methanol being injected. What will be the dead time? So how much time will it take to travel the point of injection, that is the point of loading, till the point it is out. So that point is called as your T0. T retention is your retention factor, at what point this will come out, and this is your peak height and peak area. Again you can do the same thing, you can inject measured amounts. 20 microgram, 40 microgram, 60 microgram, 80 microgram and so on, create a standard curve based on the peak area and then plot the unknown, you will get the concentration of your bioactives. So let's see a HPLC graph of vasicine and vasacinone. So in this case they have used a reverse phase column. Now what is reverse phase? When I say normal phase, my stationary phase is polar, my mobile phase is non-polar. In a reverse phase column, my stationary phase is non-polar, generally C18, meaning a 18 carbon hydrocarbon has been attached to my silica, making it extensively oily or lipophilic. So I need a very polar mobile phase. So my mobile phase is acetonitrile and phosphate buffer, which is nothing like a watery solution, and a flow rate of 1 ml per minute. So what happens is when I inject it, you can see this is just the standards being injected and they get resolved very well. So vasicine about 100 microgram per ml and vasacinone 100 microgram per ml. Now they both are in equal quantities, but can you see their peak height is different? The reason is the amount of light each molecule structurally kind of absorbs is different, and their absorbance at the same wavelength, that is 300 nanometers, is different, and that is why despite same concentration they will have a different height and maybe a slightly different area as well. So I put the standard concentration. After this I will inject my extract, then I will see how much is the area under curve for the extract, and basis that I can quantify this. So here are a few references that you can go through or which have helped us in preparing this session, and thank you everyone for your patient listening.